G'day there, you're watching the Aussie Boom Guru, and today we've reached part 10 of my feasibility series in Revit and Dynamo. Today we're looking at refining our initial study. So we've looked at our feasibility study, but in our last part we've just analysed our sun hours. So how many hours of sunlight are all our apartments going to receive, likely based on our mass. So now we're going to refine the study to make a better assumption about whether our design will actually comply to the requirements. We're also going to look at Power BI in the next part as well. So we've set up our sensor grid a few parts ago now, and we've been using it for a couple of tutorials. So we looked at it in our last part for solar analysis, so basically checking if sun rays could actually reach the building through our site at certain times of day. So looking a little bit like this, but we did only take samples on the hour, every hour, so this isn't actually refined enough for many studies that we undertake in Sydney. So we ended up with a result that looked a little bit like this. So we ended up with basically a percentage breakdown of size of the building and also an overall assessment of whether we met the two requirements of what we call SEP 65 in Sydney. So what I've done is I've just done some really generic apartment layouts, and instead of doing sensors across the entire building, what I've done is removed all the sensors except for the ones in the likely living room areas in a potential apartment layout. Now I know this isn't a very pretty layout, it's not, architecturally considered, it's just a really generic knock-up, but what's important is the sensors are all placed at the location of living rooms, because in our last study we noticed that the south face of our building got no sun at any time of day in winter. Likewise, we also have our other option as well, our half site, which I've also set up some locations for too. So we'll look at the results of that at the end of our study and see if our designs actually comply. So sun hour is just a requirement in Sydney under our SEP 65 requirements. So basically our living rooms for at least 70% of our apartments in the middle of winter need to receive 2 hours of direct sunlight, and also a maximum of 15% are allowed to receive 0 hours total. And SEP 65 requires 15 minutes of continual exposure at the very minimum. So we're going to refine the script today to measure 15 minutes in continuity. So essentially we're going to be looking for intervals at 15 minutes at a time. And you can see here, for example, if we have an interval that reaches across 2 rows of 15 minutes, we know that at least it's very likely between this period of time that there is continuous sunlight during that 15 minutes. We're not going to be able to pick up every single result. So for example, if there's a time span that crosses one barrier of 15 minutes, but it actually covers, say, 10 minutes here, then 5 minutes there, it's going to be basically managed out as a non-result. So you could refine this to measure like every minute if you want it to be really precise and find exactly all those 15-minute intervals you're trying to find to achieve your compliance. As well as this, you can see that if we had, like, say, 3 true results, it's not 45 minutes of sunlight, it's half an hour of sunlight, because we don't know if it goes all the way through to the next 15-minute barrier if it doesn't reach this next point. Likewise, if we have a result like this that would go through one gate but doesn't reach the next one, it's managed out as a false. So essentially this is how we can refine how much sunlight we're receiving. So if we have like n consecutive number of true results for a successful sunlight, if we take 1 from that and we times it by the 15 minutes of sunlight, and then we divide the sum of those totals by 4, we're going to receive a more accurate sunlight hours for that particular sensor, in which case it represents the actual apartment itself. So we're going to use Dynamo to process this. And as I've said before, Grasshopper and Rhino are probably better for this study. There's a good guide at the website Parametric Monkey. Highly recommend you check it out. And we'll be using the EPW file again from our original script, which is a weather file, which you can get from Energy Plus. And we'll be using Ladybug again from our previous script, which you can download from the package manager. And we'll be using some custom nodes today, specifically Zebra's if node and some Ladybug nodes. This is all carrying on from my previous part, so feel free to watch that if you haven't already. And we'll be using Dynamo 2.0.3, so highly recommend you use this version. If not, at the very least, you'll need version 2, I believe. But without further ado, let's actually go back to our feasibility study and our sun analysis. So you can see here, this is just a floor plan that I've just drawn up with filled regions. So I'm roughly trying to test the potential floor plate of my building. Again, not the most architecturally beautiful floor plate. There's probably a lot more building form that we can experiment with as well. Because some of these apartments are obviously very long and don't get a lot of glazing opportunity, which probably means they may not comply anyway. But we're just testing them purely for the sake of solar analysis today. So if we just jump into 3D, I'll jump into 3D on my my 1B study, which is my full site. You can see that I've limited the number of sensors we're dealing with just to the sides of the buildings with the living rooms. So I'm no longer dealing with 1,500 sensors, I'm dealing with about 200. Still quite a lot to process because we're going to be increasing the number of vectors that we need to sample. So if we go back into Dynamo to our script that we built in the last part, which you probably recall if you see it, I won't explain how it all works now because hopefully you've seen the last part. So the first thing we need to do to actually change our script is introduce the minutes factor to our range. So what we're going to need for that is just a range between 0 and 45 with a step of 15, which will give us 0, 15, 30, and 45. Because we also want to introduce the increments of 15 minutes to our time range because we're testing every 15 minutes now. It's really important to note that this needs to be a cross product in its lacing in order to generate all the possible times between the mix of the hour range, the day, and the minute range. What I'm just going to do is just jump ahead a couple of steps and freeze a couple of things. So I'm going to freeze my model geometry, which essentially will freeze a majority of our script. I'm also going to freeze my element location for my nodes. It's important to note that we've already got option 1B being filtered out and also the tower component being filtered out. So I'm still retaining the data in my sensors that tells me that in order to limit the number of sensors that I'm dealing with. Okay, so at the moment this will give us a time range between 9 o'clock to 3 with 15-minute increments. However, the problem is that we're not sampling data between 3 and 3:15, so essentially we don't know if we have a time slot that crosses 3 o'clock, we can't test it. So what we need to do is add one more time slot to the end of our vector range. So we need to add the vector for 3:15 in this case, or 15 minutes after this time here. So what we're going to do is generate another arrow view. And the only difference is, in this case, the minute will be 15, and the hour will not be the range. Instead, it will be the end hour. And essentially this will just introduce one additional time to the test range. And from there, we also need to generate another sun path. So we'll just move this back and I'll just generate an additional sun path. The only difference being that we're only feeding in the hour of year from this. After that, we need to add to the end of our vector list that item. So I'll show you how that looks in a second once I've added the item. Sorry, my Dynamo is running a little bit slow today. Add item to end. So we want to add this vector to the end of this list, and then we flatten that list instead. Okay, so I'll run what we have to this point, which all that will happen now is it will collect all the sensors and it will collect all the vectors, and everything else is frozen currently. So if I run this, we should expect to see a list of all those vectors combined. I think from there, the next step that we're going to do is we're going to augment how we deal with our results as they come out at the end. So at the moment we'll have 29 vectors. We originally had 28, and then we add on 315 and we get the 29th vector. So what we're going to do now with these is clash them against our site. So I am actually going to unfreeze this portion of my script, and I'm also going to unfreeze this portion of my site, and I'm going to run everything up until the very last minute, and then I'm going to disconnect my formulas here, and I'm going to collect these samples in this position. So I'll probably skip ahead because this is obviously going to take a little bit of time to collect all this data, but then I'll get back to you and I'll reactivate the video when the script finishes running. Okay, so our results have just finished processing. You'll recall that originally we turned all our trues and falses into zeros and ones. So basically a 1 represented a successful ray of sun reaching our sensor, and a 0 represented a non-successful ray. So you can see here, for example, that the first 11 rays are successful in the vector pass and the rest of them aren't. Each list has 29 results in it, as you'd expect, and sometimes there'll be gaps between the 1s and the 0s, depending on the list structure. So sometimes you'll get sun in the morning and the afternoon, but not in the middle if there's something in the way. So what we need to do is actually find out how many consecutive 15-minute intervals are clumped together in our lists. And this is actually quite a difficult thing to do. So what we need to do first is find all the indices of 0, or an unsuccessful ray. So we're just going to look for all indices of, sorry, my search function in Dynamo is incredibly slow today. So we'll do all indices of. I think because I'm handling so many results, it's just slowing everything down. So bear with me. Okay, so we're doing all indices of, and we're going through each sublist. So we're going to work at level 2 in our list, and we're going to look for 0. And from these indices, we're going to be able to process basically positions to break our lists at. But you can see that we're finding the indices in each list where a 0 occurs. So what we want to do then is we want to add 1 0 to the front of each sublist. And we're going to take away the result to find out the space between each respective indice of 0. So we're going to take our list and we're going to add 0. And we're going to add it at the front of each sublist. So we're going to have to work at level 2 again. And then we're going to set up a minus node. So we're going to take away one list from the other. So we'll take our original list from our new list with a 0 in front. So basically we're finding the difference between each respective index to find the distance between each of those occurrences. So we should expect to get basically a range. So you can see that we have 11 indexes of false, and then 1, 1, 1, 1, 1 between each index of true. So that's how we can process that distance. From there, what we need to do is we have to count the number of vectors we're dealing with. So in this case, we're just going to go back and call on a list count node, and we're going to feed that back to the number of vectors that we generate. So we'll take this all the way back to our reversed vectors, and we'll have 29 of them. That's it. That's so if we change our time range, it still responds. And the reason that we're doing that is we're going to sum the list of each of those, because we need to process the very first space in our list, because we're going to apply a list chop, essentially. What I'm doing may not make a lot of sense on the surface, so just bear with me and you'll see sort of what I'm trying to do. So I'm going to sum each sublist in here to find out how many hours we're dealing with in total, and then we're going, or how many hours we're working between. I'm just going to make a code block actually, and I'm just going to call that code block, I'm just going to make that code block the count of vectors minus the total number of elements we're dealing with. So we're going to go count and sum. So we're going to end up with a list of basically a sum of each. So this is basically the distance between, I think from what I recall, this is the distance between the first interval. So if it's basically here to detect a list that is full of falses, because otherwise we don't end up with a way to detect those. So if I go to index 4, for example, I have an empty list. So this is our way to detect where we have those lists where everything is successful. And what we're going to do then is we're going to add an item to the end, and we're going to add the index to the end of the list. So we're going to go in, and at level 1, we're going to add this index at level 2. So our list is going to be this one, and our item is this number here. So this will represent basically the distance for lists. So now if I go to list 4, you can see we end up with 29, and the rest of them we end up with either 1 or basically 1 or 29, depending on whether it's a full list or if it's a list where you have variance in the length of lists. And from there, we're actually going to use this to chop our original list, so that we can actually break our lists into sublists of either true or groups of false. Because we basically found out where all the groups occur of false. So we're going to make this level 2, and we're going to make our list level 2. And the list that we're going to call on is our original list of results back here. So now if I apply this chop, you'll see that each respective sublist has been broken up into groups of 1s, and then the 0s are all broken off into their own individual sublists. So this is how we can detect groups of successful results, essentially. So you can sort of see when 1s occur, they're all grouped together. Okay, so that's probably the hardest part dealt with. What we need to do now is we need to sum each of those sublists. So we're going to use list map to apply a sum function to each sublist in the sublist itself. So we're going to apply a list map, and then we're going to get another math sum. But in this case, we're going to apply it on a map basis. And this this will collapse our lists into summed lists. should take just a little bit to process. It's just running a lot of functions, a lot of elements. Okay, so now you can see that these groups of ones have been grouped together, and all of zeros have just been collapsed. So now we can see how many groups are occurring of true sun rays that are successful. So what we need to do now is actually manage out our zeros. So we're going to set up a mask to check when the condition is greater than 0. And we're going to apply that on a Boolean mask basis. So we're going to filter by Boolean mask. And this will manage out all of our 0 lists. Okay, so we're going to filter that list by this mask. And our ins should represent our successful numbers that are greater than 0. And there you go, you can see that all our numbers above 0 end up here. And then all the respective components that are made up of zeros get broken into out. At that point, we need to take the results of those and take away 1. And the reason that we're doing that is essentially because we want to deal with everything except for that last increment, which doesn't reach the full 15 minutes. So we're taking 1 away from all these results in order to get the true amount of full spans of 15 minutes. And what we do with these lists then is we sum this again, and this will give us our total successful increments of 15 minutes that is achieved during our range of time. So essentially these all represent how many increments of 15 minutes we're dealing with. And that should be done. And then from there, we just need to divide this by 4 to find out how many hours we're dealing with that are successful. And you can see that sometimes it's not a full hour that we're dealing with. Sometimes it's only 2.5 hours or 1.5 hours. So we need to apply a floor to our function in order to round it down to the nearest whole number. Because obviously 1.5 hours doesn't count. You only achieve 2 hours if you achieve 2.5 hours, for example. So we're going to apply the floor function, and that will force it to be rounded down. And from there, we should end up with a list representing the true number of sun hours based on 15-minute consecutive intervals. So quite difficult to achieve, quite a complex function. Took me quite a while to figure it out, I'll be honest, but we got there in the end. So some of that may make sense to people, some might not, but if you follow that logic, you'll end up with the right results. So you can see there that we have 260 sources that we're dealing with, and we end up with 260 numbers as well. So that's perfect. So now we can feed these back into our sensors. So essentially I'm going to take my result node with my set parameter by name, and we're going to feed those numbers into the values. And I'm going to go back and get my elements as my sensors right before I got their location. And from here, we should be able to update our sensors with their true number of sun hours. So I'm just going to run my script. And there we go. We get our true number of sun hours by sensor. And we can see that we're actually getting quite a few that are being blocked a lot more than our original results were showing us, because we've done a better calculation now. And we can see that some of these were actually not as good as we thought they were once we consider 15-minute intervals. I remember these were green in my previous study. So what I'm just going to do is just jump into a model where I've undertaken 2 studies. So I think it's this one here. So I've done 2 studies for a half side option and a full side option using this script. So essentially we've got our sun study for what I call 1B, which is our full site. So we've just run that there. And we've also got one for our half side option as well. And you'll see the half side option is actually not very good. There's a lot of sensors that are coming up with 0 hours. Despite the fact that we've tried to arrange our apartments to counteract this. So if I go back to my sun hour total for my full site option, I can see that I've only got 1.9% of my apartments receiving 0 hours, which is great. And from there, I've got, I think, 6% of my apartments are less than 2 hours of sunlight. So we're well over our requirement. But if I go to my option 2B, which is for my half site, you can see that we have more than 15% of our apartments not achieving the requirement of at least 1 hour of sun, because 15% is our maximum threshold. So we're just over our minimum requirement But we're still over our 70% requirement for our apartments, because you can see 21% of our apartments have less than 2 hours of sunlight during the winter. So, but you can see that the full site option is much better, because we've managed to distribute more of our apartments to the side of our building and move the living spaces to more desirable locations. So that's how you can undertake a more detailed analysis of the sun hours, but it's a lot more complicated, obviously, and it will take longer to run because you're testing more vectors. But hopefully that makes a little bit of sense. The next part we're going to do is we're going to look at Power BI. So what you're going to need to do is actually collect a lot of your data from your model. So things that I recommend collecting in Excel are your mass floor schedules, the count of your apartments, or what you project the number of apartments to be, and potential financial values associated to what they could be sold for based on their height and also their position and their size, maybe their typology. I also recommend collecting the table of sun hours but maybe break it up by floor or break it up by face. Find something that you want to measure it based on, because we'll use those in the next part. And generate a building section. I do have a great video that deals with a tool called the Synoptic Panel that is worth checking out, because that one will sort of show you how to turn a section into a Power BI view. So if I just go to my channel here, and I'll just go to, I think it's Revit tutorials. So it should be this one here, Revit floor plans into Power BI. So if you have a look at this video, basically it will show you how to generate views in Power BI. So I'm going to skip actually generating the section for Power BI and just bring it in at that point. So have a look at this video and it will show you how that process works. But we're going to tie that into our levels and our program so that we can successfully visualize our design in Power BI. Anyway, hopefully I'll see you in the next video where we finish up our series. If you've got any questions or queries about this, feel free to leave them down below. I know it's quite complicated, so I expect there'll be some queries over time. And hopefully I'll see you in the next video. If you're not already following and subscribing, feel free to do so. And see you next time. Thanks. Take care. Bye.